All right, so let's look at some energy and stoichiometry. This tends to be a little intimidating for students, but not actually all that tough, right? Very, very practical, whether we're thinking in terms of eating and how much energy there is in food and that kind of stuff, or whether we're talking about those little heat packs where you crack a thing and cause a chemical reaction to take place and how much energy is it going to do to how much energy there is in cars, right? Energy is a huge deal for us. And the way we store a lot of energy and use a lot of that energy is through chemical reactions and stuff, right? So whether it's plants and solar cells and there's lots of ways that energy and chemistry kind of roll in together and stuff. So the nice thing, right? So the amount of energy released or absorbed by a chemical reaction is a predictable set amount, right? It's a given amount all the time. That means we can do stoichiometry, whether it's with solid chemicals, gases, solutions, and with energy, right? To do stoichiometry with energy stuff, we're going to need a balanced reaction with the amount of energy gained or lost, right? Absorbed or released or whatever. Yeah, it's not like my handwriting's only bad on the computer, right? So we're going to need a balanced reaction, and we're going to need the amount of energy gained or lost. The amount of energy we can show two ways. We can do this, which is a thermochemical equation. Ooh, right? Thermo, heat, chemicals equation. So this is a thermochemical equation. So that's a $10 word you can use today. When mom's like, so what did you do today? You can be like, well, we worked on thermochemical equations, and then she'll be like, wow, right? So anyway, you can do it this way, or they can give you a reaction and then list the delta H. If we write it as a product, this is going to be released like an exothermic reaction. If we write it like a reactant, it's absorbed, right? So overall, this would have a negative delta H, right? Since this is exothermic. So a negative delta H corresponds to exothermic. If we write it as a product, that corresponds to exothermic. So it's released, right? So here's our reaction. This is iron rusting. If I take iron and react it with oxygen, it is an exothermic reaction, right? It's going to release energy. Now, you don't notice iron rusting being hot because it happens really, really slowly. But if it happened quickly, it would. And that's what sparklers do, right? Sparklers have iron, little tiny bits of iron stuck on them. You burn them, and they release a whole bunch of energy. So when we're going to do this, we're going to start with our 30 grams of iron. And then we're going to say, well, it's 55.85 grams of iron for every 1 mole of iron, right? And I know like Higgins likes to do the little bracket things like that, so that's just fine. And then this part was done for us. Once we change it to moles of iron, it's a mole bridge. So 4 moles of iron comes from right here for every 1648 kilojoules. So there's no molar mass for energy. So the standard is not a 3-step problem. The standard is a 2-step problem for these. So it's actually easier. There's only 1 molar mass, right? So mathematically, what we're going to do here is 30 times 1648 divided by 55.85. Multiply by everything that's on top. I ignored the ones. Divide by everything that's on bottom. Oh, I forgot to hit also divide by 4, right? Because there's a 4 down there too. So it is 221 kilojoules of energy, and it is released because this is an exothermic reaction. So if we did this, that's how much energy would be released. We're going to do stuff with that energy next week with the Q equals MC delta T equation. You might remember those from last year, right? So you do a regular molar mass kind of thing, and then the energy just goes in as a mole bridge. So I'll go ahead and do a couple more. If you get it, certainly feel free to work ahead of me and stuff. How much iron 3 oxide do you have to make in order to make 3,000 kilojoules of energy? So now we're talking about the energy first. We know about the energy. We're asking about the iron oxide stuff, right? So we're going to go the opposite direction. So we'll take our 1648 kilojoules so that we can cancel kilojoules because the kilojoules is what we know about. But now we're going to change that to iron 2 oxide. So that's a 2 mole bridge, 2 moles of the Fe2O3, right? So this is just a mole bridge. Just like this one, notice it's a different mole bridge because we're asking about a different chemical. Here we had iron, here we have iron 3 oxide. So we do our mole bridge and go there. And then I need a molar mass for iron 2 oxide. So I'm going to do 55.85 times 2 plus 16 times 3. 16.00, I'm just not filling those in, but right, we keep those sig figs. So that's going to give me, for every 1 mole of Fe2O3, it is 159.70 grams of Fe2O3. All right, so again, 2 steps is kind of the standard here. So 3,000 times 2 times 159.7 divided by 1648 gives us 581 grams of Fe2O3. Now, again, what did this just tell us? They ask us how much iron 3 oxide we would need to make in order to also make 3,000 kilojoules of energy, right? So we knew we wanted to make 3,000 kilojoules of energy, so that was what we started with. We did a mole bridge to get to moles of the chemical we wanted to know about, and then a molar mass to get to that, right? How much of this did we need in order to get that much of that? Since they're both products, we talked about making both of those, right? This one was exothermic again, because we made the energy as a product. We look at this one, now we see energy listed as a reactant, right? Is this endothermic or exothermic? Since we listed as a reactant, this is endothermic, where this one would have had a negative delta H, negative 1648 would be our delta H on our reaction, and our energy graph would look like this. Downhill, this one, our energy graph would look uphill, right? And it would, this change here would be 27, right? Because it's 27 kilojoules of energy in order to dissolve this stuff. That's what this is looking like, dissolving. If I dissolve ammonium nitrate, that's an endothermic process. So how much energy is needed to dissolve 5 grams of ammonium nitrate? So if we have 5 grams of this, how much of this am I going to need to do? So this is where normally in a regular class, I would kick students to go do this by themselves. I think it would be wise to try this one on your own. But if you're not sure what to do, I'll go ahead and work through it. So 5 grams of ammonium nitrate, we're asking about energy. So I'm going to go from grams of ammonium nitrate to moles. So 14.01 times 2 plus 4.04 for the hydrogens plus 16.00. So you see my sig figs there, times 3. So it is 80.06 grams of NH4NO3 for every 1 mole of NH4NO3. And then we say, well, with this reaction, it's a 27 kilojoules for every 1 mole. So for every 1 mole of NH4NO3, it's 27 kilojoules. So we would just do 5 times 27 divided by 80.06, and that's going to give us 1.69 kilojoules of energy. Technically, I guess I have like 1 sig fig because Mr. Fred was sloppy when he was making this thing. So I'd say 2 kilojoules because we only have 1 sig fig, but right. So again, what this is telling us is it's going to have to absorb 1.69 kilojoules of energy in order to dissolve 5 grams of stuff, right? So as the water dissolves that stuff, it's going to actually get cold, right? Because the water is going to be what has to give the ammonium nitrate that energy, right? The water is the surroundings, the ammonium nitrate's the system, right? Let's see. Let's do at least one more today together. Let me move this down a little bit so we can see well enough. If the reverse reaction happened, right? So this direction happened, the ammonium nitrate coming out of solution, how much would have to come out of solution to release 5,000 kilojoules of energy? The math is not different. Students will get worked up about math stuff. The math is not different here. They're just saying if the reverse happens, it's going to release energy, just like photosynthesis and cellular respiration are back and forth reactions, right? Photosynthesis this way, cellular respiration, right? It's the same reaction, just back and forth. This is just going to be the word release here because we're going backwards, right? It would be precipitating, and that would release energy. So we're going to start with 5,000 kilojoules and say, well, for every 27 kilojoules, we're again going to ammonium nitrate, 1 mole of ammonium nitrate, and then say, well, for every 1 mole of ammonium nitrate, I apologize for being left-handed. You can never see what I'm writing. It is 80.06 grams of ammonium nitrate. right? So it's the reverse of this. It's not the reverse because they're talking about the reverse reaction. It's the reverse because they give us energy instead of mass. Here they gave us mass, so we started with mass. Here they gave us energy, so we started with energy, right? I don't know if I'm going way too fast or way too slow for you. I normally like to look at faces and see if you're starting to figure this out a little bit. So it's a lot, right? This is a big number. So I multiplied by 80.06 because that was on top, divided by 27 because that was on bottom. We've only got one sig fig again. Mr. Fred was really sloppy when he made this, but let's go ahead and keep 2 at least so we don't have to round to 10,000. So we'll keep 2 sig figs to make up for Mr. Fred. Here, we'll put a line over that. See, there was a line printed there the whole time. Right, 10 minutes. Let's try one more. I know these get long and you've probably already left because you were bored of me talking. Let's skip this top one and let's do this one. If I eat 2 grams of sugar, how many calories of energy would you have to use? Well, you might remember from health class, we have an estimate of 1 gram of carbohydrates, and carbohydrates is sugar, is 4 big C kilocalories, right? So that would be, if we've got 2, the health class estimation then would be 2 big C calories. And if you multiply, and the conversion from calories to joules is 4.184, which we'll kind of get into next week. So the rough health class version of this is 33 kilojoules. I'm curious how close we're going to come to that, right? This is the health class, like just estimation kind of thing. This is chemistry a lot more specific. So when we break down sugar, we have to breathe oxygen, and then that takes the sugar in our body, and we breathe out carbon dioxide, water, and we use a bunch of that energy, right? The energy does 2 things. It heats up our body, and it causes us to work, right? That's first law of thermodynamics. You either have to do work with it or turn it into heat. So we do a lot of that kind of thing. So 2 grams of sugar, 2 grams of C6H12O6. Well, for every 180.18 grams, you don't have that memorized? I've done way too many of these problems. C6H12O6. And then we better balance this thing. So we go 6 here for the carbons, 6 here for the oxygens. We count up, or for the hydrogens, we count up our oxygens. We're going to have to go with 6 over here. So it's 6166. So it is 1 mole of sugar, C6H12O6, for every 2,826 kilojoules. So we do 2 times 2826 divided by 180.18, 31 kilojoules. So if you looked at health class, estimation was really pretty decent, right? Health class estimated 33 kilojoules just off of 4 calories per gram, and then converting from there. This is the chemistry version that's a little bit more specific, right? Anyway, hopefully that's helpful, and keep working those problems. We'll come back, I think, tomorrow and work a few more of those. Maybe do, I don't know what we're still figuring out what we're doing tomorrow.